What if the greatest catastrophe in human history wasn't written in ancient books, but carved into the rocks beneath our feet? Across mountains, deserts, and forgotten landscapes, strange layers of stone preserve evidence of a world-shattering disaster that may have changed the course of civilization forever. Gigantic floods, unimaginable earthquakes, and mysterious extinctions. Could these silent rocks be telling a story we've overlooked for thousands of years? Tonight we're uncovering the ancient apocalypse hidden in plain sight. Before we begin, if you enjoy mysterious history, lost civilizations, and the greatest unsolved mysteries of our past, please like this video, subscribe to the channel, and turn on notifications so you never miss our next journey into the forgotten world. Let's begin. The cliff appears ordinary at first glance. A wall of layered stone rises above the landscape, its colors shifting from pale grey to rusty red beneath the changing light. Wind brushes across its surface exactly as it has for thousands of years. Rain has carved narrow channels through the rock. Moss clings to shaded cracks. Birds nest in ledges that were already ancient before the first cities appeared. To almost everyone passing by, it is simply another outcrop, another quiet piece of the landscape that seems as permanent as the horizon itself. Yet hidden inside those silent layers lies the record of worlds ending. One thin band of dark sediment marks the afternoon when sunlight disappeared beneath a sky filled with ash. Another preserves the chemical fingerprint of oceans that suddenly lost much of their oxygen. A different layer contains microscopic crystals formed during unimaginable impacts that shook the entire planet. Still another records the slow drowning of forests beneath rising seas, while nearby fossils reveal animals that never walk the earth again after that moment. None of these events were witnessed by historians. None were described in written chronicles. Long before humanity learned to carve symbols into clay or ink onto parchment, the rocks themselves became the only surviving archive. That archive is astonishingly complete, yet remarkably difficult to read. Unlike a library, it has no orderly shelves. Pages are torn away by erosion. Entire chapters disappear beneath younger sediments or sink beneath oceans. Heat twists the original record until it barely resembles its former shape. Earthquakes fold once horizontal layers into impossible angles. Rivers carry fragments hundreds of kilometers away from where they first formed. Every geological process edits the story while simultaneously preserving parts of it. Reading this archive requires extraordinary patience because every answer usually creates two new mysteries. For centuries, people looked at mountains and cliffs without realizing they were standing before the greatest historical document ever assembled. Many cultures explained unusual rocks through stories of giants' floods, divine punishment, or mythical battles. Those stories often reflected genuine attempts to understand landscapes that seemed too strange to have formed gradually. Massive boulders resting alone across open plains appeared impossible to explain. Seashells embedded high in mountain ranges challenged every simple assumption about the world. Forests turned into stone looked like nature itself had been frozen by supernatural forces. Only gradually did another possibility emerge. Perhaps the rocks were not random objects scattered across the surface of the earth. Perhaps they were records. That realization transformed human understanding more profoundly than almost any single scientific idea. Instead of imagining Earth as an unchanging stage upon which history unfolded, scholars began recognizing that the stage itself possessed a history vastly older than humanity. Civilization suddenly occupied only the final pages of a story stretching back billions of years. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. Once that perspective settles and familiar landscapes become almost impossible to see the same way again. A peaceful valley is no longer merely a valley. It may be the floor of an ancient inland sea. A desert may once have supported rivers filled with fish crocodiles and lush vegetation. A mountain summit may preserve sediments deposited quietly beneath tropical oceans long before the first mammals evolved. The ground beneath every step becomes less like solid earth and more like a layered memory. The oldest portions of that memory reach back into a world almost beyond imagination. Earth itself forms roughly 4.5 billion years ago through countless collisions among growing planetary bodies orbiting a young sun. The surface remains molten for immense spans of time. Volcanoes dominate nearly every horizon. Asteroids strike with terrifying frequency. Oceans slowly condense from cooling steam and water delivered by countless impacts. The earliest crust forms only to be destroyed and recycled again and again. Almost none of those first chapters survive intact. Earth is unusually active among rocky planets. Continents drift. Ocean floors spread apart before disappearing beneath one another. Entire mountain ranges rise and later erode into sediment. This continuous recycling destroys enormous amounts of the earliest geological record. What survives today represents only scattered fragments preserved through extraordinary circumstances. Even these fragments reveal that our planet has never been truly stable. Stability, in fact, may be one of the greatest illusions produced by human lifetimes. People naturally measure permanence against the span of a few generations. Mountains appear eternal because they barely change within a century. Coastlines seem fixed because they shift only slightly during a single lifetime. Forests recover after storms. Rivers return to familiar channels after floods. Daily experience teaches continuity. Geology teaches something else entirely. Given enough time, every landscape changes beyond recognition. Entire oceans vanish. New ones open. Continents collide and merge before breaking apart once more. Deserts become rainforests, while rainforests become deserts. Ice sheets advance across half a continent before retreating again. Species dominate for millions of years before disappearing almost completely. Even the atmosphere itself has transformed repeatedly, sometimes slowly, sometimes with astonishing speed. Yet these transformations rarely announce themselves in ways humans easily recognize. Some unfold over millions of years, too gradual for any individual observer. Others occur with shocking suddenness. A volcano erupts, an asteroid strikes, a fault ruptures beneath a city. An enormous landslide reshapes an entire valley within minutes. A tsunami reaches coastlines faster than fleeing populations can escape. The rocks preserve evidence of both extremes. Some layers represent countless generations of quiet accumulation. Tiny shells settle gently onto ancient seafloors, building limestone grain by grain. Dust drifts across broad floodplains. Coral reefs slowly expand beneath warm, shallow seas. Each millimeter records years, decades, sometimes centuries of calm conditions. Then the pattern abruptly changes. A thick, chaotic layer appears where none should exist. Giant boulders lie mixed with fine mud. Broken trees become buried beneath marine sediment. Ash blankets forests hundreds or even thousands of kilometers from its volcanic source. Chemical signatures shift almost instantly. Entire fossil communities vanish between one layer and the next. Something extraordinary happened. Determining exactly what happened is rarely straightforward. The evidence remains incomplete because nature seldom preserves perfect records. Wind removes sediments before they harden into stone. Rivers carve through older deposits. Later disasters overwrite earlier ones. Scientists often reconstruct ancient catastrophes using tiny clues scattered across different continents, assembling them much like detectives rebuilding an event from isolated fragments. One cliff preserves volcanic ash. Another contains fossil pollen. Ocean sediments reveal changing chemistry. Ice cores preserve atmospheric gases. Together they begin telling a coherent story that no single location could reveal alone. Sometimes those stories overturn ideas that had stood for generations. Features once attributed entirely to slow erosion turn out to record immense floods. Rocks dismissed as ordinary sediments reveal evidence of global climate collapse. Tiny grains of shocked quartz expose impacts so violent they altered life across the planet. Ancient coastlines discovered far inland demonstrate oceans that no longer exist. Each discovery expands the archive while reminding researchers how much remains unread. Perhaps the greatest surprise is not that Earth has experienced catastrophic episodes. It is that catastrophe appears repeatedly throughout its history. Again and again, the planet crosses threshold where familiar environments disappear and entirely new worlds emerge. Some recover quickly. Others require millions of years before ecological complexity returns. Human civilization occupies only the latest moments of this immense sequence. Written history fills a fraction of the final page. Everything before it survives almost entirely in stone. The cliffs, mountains, deserts, and seafloors are therefore far more than scenery. They are memory made solid, preserving moments when the world changed forever, without anyone being there to write what they saw. Every layer waits patiently beneath open skies holding secrets older than language itself, inviting anyone willing to learn its strange language to glimpse apocalypses so ancient that only the earth still remembers them. The illusion of permanence begins to fade the moment the rocks are viewed not as scenery, but as moments frozen in time. A granite peak towering above the clouds no longer seems immovable, when it becomes clear that it was once buried deep beneath another mountain range that has long since vanished. A broad plain stretching to the horizon is no longer simply empty land, when its sediments reveal the slow passage of rivers that disappeared tens of millions of years ago. Even the quiet ocean, which appears endless and familiar, is only the latest arrangement of waters that have repeatedly opened, closed, expanded and vanished throughout Earth's history. To human eyes, the planet appears remarkably stable. The continents occupy familiar positions on maps. Coastlines shift only gradually. The seasons arrive with reassuring regularity. Most people live and die believing the world they inherit is essentially the same world their descendants will inherit. Geological time offers a very different perspective. It reveals a planet that never truly stops changing, where stability is often nothing more than an unusually quiet interval between episodes of transformation. The forces responsible for this restlessness operate mostly out of sight. Far beneath the continents, heat left over from Earth's formation continues to circulate through the mantle. This slow movement is almost impossible to notice directly, yet it drives the enormous tectonic plates that carry entire continents across the surface. They move only a few centimeters each year, roughly as fast as human fingernails grow, but over millions of years that seemingly insignificant motion rearranges the face of the planet. The evidence survives everywhere for those who know where to look. Mountain belts separated today by thousands of kilometers contain nearly identical rock sequences, fossils and mineral deposits suggesting they were once joined together before oceans formed between them. Ancient coastlines now lie high above sea level, while marine fossils appear in deserts hundreds of kilometers from the nearest shore. Vast layers of sandstone preserve ripple marks left by beaches that disappeared before dinosaurs ever existed. What survives in the geological record suggests that Earth's geography has always been temporary. One of the most remarkable chapters in this ongoing transformation is the repeated assembly and breakup of supercontinents. Rather than remaining scattered indefinitely, the continents periodically drift together into immense landmasses before slowly fragmenting apart once more. The most famous of these is Pangaea, which existed roughly 250 million years ago. At that time, nearly all major continental crust formed one enormous landmass surrounded by a global ocean. Life on such a world experienced conditions unlike anything familiar today. The interior of Pangaea lay so far from the moderating influence of the sea that enormous deserts stretched across thousands of kilometers. Seasonal temperature swings were extreme. Rivers followed courses that no longer exist. Winds traveled across uninterrupted landscapes of astonishing scale. Animals migrated through territories that would later become separate continents divided by oceans. Eventually, the immense landmass began to fracture. Deep cracks opened across its surface. Magma rose through the thinning crust. New ocean basins slowly formed, widening year after year as fresh seafloor emerged between separating continents. The Atlantic Ocean itself began as one of these fractures, growing so gradually that no living creature could perceive the process, yet relentlessly enough to create an entirely new ocean basin. The rocks preserve this transformation with remarkable precision. Lava flows record the opening of rifts. Magnetic minerals trapped inside cooling basalt reveal the direction of Earth's magnetic field, allowing scientists to reconstruct the movement of tectonic plates across immense spans of time. Fossils found on opposite sides of modern oceans demonstrate that species once lived together before continental separation isolated their populations. It is one of geology's greatest achievements that such slow movements can now be measured with extraordinary confidence. Yet tectonic motion does far more than rearrange continents. It also creates the conditions for many of Earth's greatest catastrophes. Where plates collide, mountains rise as crust crumples upward. These mountain-building events, known as erosionies, reshape entire regions over millions of years. At the same time, enormous stresses accumulate along faults buried deep beneath the surface. Most remain locked for centuries before suddenly releasing their stored energy in devastating earthquakes. Although human history records only a small fraction of these events, ancient fault scarps and disturbed sediment layers reveal that far larger earthquakes have occurred repeatedly throughout geological history. Elsewhere, one plate descends beneath another in a process called subduction. As oceanic crust sinks into the mantle, water trapped within the descending rocks lowers the melting point of surrounding material, generating vast reservoirs of magma. These feed volcanic arcs that can remain active for tens of millions of years. Every explosive eruption adds another page to the geological archive, depositing ash that may later become one of the most useful markers for reconstructing ancient events. Even seemingly tranquil landscapes often conceal violent origins. The rolling hills of many regions are actually the worn-down remnants of mountain ranges that once rivaled the modern Himalayas. Wind, rain, frost, rivers and glaciers gradually grind towering peaks into sediment, carrying the debris toward distant seas where entirely new layers of rock begin forming. Those sediments may eventually harden into sandstone or shale, only to be lifted into future mountain ranges as tectonic cycles continue. This endless recycling makes Earth unique among the rocky planets of the solar system. On worlds such as the Moon or Mercury, ancient impact craters remain largely unchanged for billions of years because little geological activity erases them. Earth behaves differently. Its surface constantly renews itself. Oceans consume old crust while volcanoes create new crust. Mountains rise only to disappear. River valleys migrate. Coastlines advance and retreat. The very evidence of ancient disasters is often threatened by the same forces that created it. Scholars still debate the exact timing and details of many tectonic events because the record is rarely complete. Entire sections of crust have been recycled back into the mantle, permanently removing pieces of Earth's history. Other rocks have been altered by heat and pressure, until their original features become difficult to interpret. Each new discovery refines previous reconstructions rather than providing final answers. Geology is less like reading an untouched manuscript and more like restoring a damaged library where many pages have already been lost. This realization changes how catastrophe itself is understood. An apocalypse is rarely an isolated event. More often it emerges from slow processes operating for millions of years before reaching a critical threshold. Continents drift almost imperceptibly until mountain ranges collide. Magma accumulates unnoticed until volcanic systems awaken. Faults remain silent until accumulated stress exceeds the strength of the rocks holding them together. The apparent suddenness of disaster often conceals an immensely long preparation hidden beneath the surface. By the time the first forests spread across the continents and early animals adapted to life on land, the planet had already experienced countless cycles of destruction and renewal. The foundations of every future ecosystem rested upon landscapes shaped by earlier worlds that no longer existed. Layer upon layer, age upon age, Earth quietly built an archive of forgotten transformations. Then, from time to time, something happened that exceeded even the enormous power of shifting continents. The ground still trembled, but the greatest changes came from above. Ash darkened the skies, sunlight faded, and entire regions disappeared beneath clouds of volcanic debris. In those moments, the rocks began recording a different kind of apocalypse, one that unfolded not over millions of years, but within days, months, and a few unforgettable years that altered the course of life itself. The first signs are almost easy to ignore. Deep beneath a mountain that has slept for centuries, molten rock begins forcing its way upward through narrow fractures in the crust. Tiny earthquakes ripple through the surrounding landscape so small that only the most sensitive instruments would detect them today. In the ancient world, no one possesses such instruments. There are only unusual tremors beneath bare feet, springs that suddenly grow warmer, unfamiliar gases drifting from cracks in the ground, and animals behaving in ways that seem strangely restless. Most of the time, nothing follows. But every so often these subtle warnings mark the beginning of one of the most powerful natural events the planet can produce. Volcanoes occupy a curious place in Earth's history. They are both creators and destroyers. The same eruptions that bury entire landscapes beneath the ash also build new islands, enrich soils, and release gases that have helped shape the atmosphere over billions of years. Without volcanic activity, Earth would almost certainly be a very different planet. Yet some eruptions become so immense that they alter climates, ecosystems, and even the course of evolution itself. The geological record preserves these extraordinary moments with remarkable clarity. Thick blankets of volcanic ash settle over forests, rivers, lakes, and coastlines, creating time capsules that capture landscapes almost exactly as they existed on the day disaster arrived. Leaves fall where they grew, insects become entombed beside flowers. Footprints remain undisturbed beneath fine layers of ash. Entire communities vanish beneath deposits that eventually harden into stone, preserving details that ordinary erosion would have erased forever. One of the best-known examples comes from the eruption of Mount Vesuvius in the 1st century, which buried the Roman cities of Pompeii and Herculaneum. Although this event belongs to recorded history rather than deep prehistory, it offers a rare glimpse of processes that have occurred countless times across geological time. Ash fell in waves, roofs collapsed beneath accumulating weight. Pyroclastic flows, searing clouds of gas ash and volcanic fragments, travelling at extraordinary speed, swept across the landscape with devastating force. Everything happened within hours, yet Vesuvius, destructive as it was, represents only a modest eruption compared with some preserved in much older rocks. Across Earth's history, there have been eruptions so vast that they cannot easily be compared with anything witnessed by modern civilization. These are the eruptions of supervolcano systems capable of releasing thousands of cubic kilometers of magma in a single eruptive episode. Rather than building steep volcanic cones, they often leave behind enormous depressions called calderas, formed when underground magma chambers empty so rapidly that the land above collapses into the void. The eruption that created the Yellowstone caldera approximately 630,000 years ago is one such event. Although Yellowstone remains an active volcanic system today, its largest known eruptions belong to the distant past. Ash from these eruptions spread across much of North America, carried by high-altitude winds over astonishing distances. Layers only a few centimeters thick, found hundreds or even thousands of kilometers away, still allow geologists to identify the event with remarkable precision. Even larger eruptions are recorded elsewhere. The Taupo volcanic zone in New Zealand, the Toba caldera in Indonesia, and ancient volcanic provinces now deeply eroded, all preserve evidence of explosions that transformed regional landscapes almost beyond recognition. Among them, the eruption of Toba approximately 74,000 years ago has attracted particular attention. The eruption expelled enormous quantities of ash into the atmosphere, creating one of the largest known volcanic events of the Quaternary period. Ash settled across much of South Asia and reached as far as the Indian Ocean. Sulfur-rich gases injected into the stratosphere likely reflected sunlight, producing a period of global cooling. Exactly how severe that cooling became remains a subject of active research. Earlier hypotheses proposed that the eruption triggered a prolonged volcanic winter that nearly drove modern humans to extinction, reducing the global population to only a few thousand individuals. This idea captured widespread public imagination because it offered a dramatic explanation for genetic patterns observed in living humans. Today, however, the evidence appears more nuanced. Scholars still debate the magnitude of Toba's climatic effects and their influence on human populations. Archaeological discoveries suggest that some groups of early humans survived in regions affected by ashfall, adapting rather than disappearing entirely. Climate records preserved in ice cores, lake sediments, and marine deposits indicate significant disruption, but no single explanation fully accounts for the complex patterns of survival observed across different parts of the world. The debate itself illustrates an important feature of geological history. Catastrophes rarely affect every place equally. Mountains alter wind patterns, oceans moderate temperatures, local ecosystems respond differently depending on existing conditions. A volcanic eruption that devastates one region may produce relatively modest consequences elsewhere. The rocks preserve these regional differences, reminding researchers that Earth's history cannot always be reduced to a single global narrative. Volcanic ash also provides one of geology's most valuable chronological tools. Each major eruption produces ash with a unique chemical fingerprint determined by the composition of the magma from which it formed. Even microscopic particles preserved within sediments can often be matched to their volcanic source. This technique, known as tephrochronology, allows scientists to synchronize geological records separated by vast distances. A layer of ash found in a European peat bog may correspond exactly to one preserved beneath an ancient lake in Asia or within Arctic ice. Suddenly, separate archives become connected. Climate shifts, ecological changes, and archaeological sites can be aligned with far greater accuracy than would otherwise be possible. In this way, volcanoes become not only agents of destruction, but also timekeepers embedded within Earth's memory. The environmental consequences of major eruptions extend well beyond falling ash. Sulfur dioxide released into the upper atmosphere combines with water vapor to form sulfate aerosols that reflect incoming sunlight. Temperatures may decline for months or even several years. Growing seasons shorten. Rainfall patterns shift. Crops fail. Forests experience stress. Marine ecosystems respond to changing nutrient cycles and altered ocean temperatures. Historical eruptions demonstrate these effects on a smaller scale. The eruption of Mount Tambora in 1815 produced what became known as the Year Without a Summer. Crop failures spread across parts of Europe and North America. Famines developed in several regions. Unusual weather patterns entered written history. Although Tambora was immense by historical standards, it remained far smaller than the greatest eruptions recorded in ancient rocks. The deeper geological record hints at volcanic episodes that endured not merely for days or years, but for hundreds of thousands of years through repeated eruptions. These prolonged volcanic intervals gradually released extraordinary volumes of lava and gas, reshaping continents while altering atmospheric chemistry. Their consequences reached beyond individual civilizations, because civilizations did not yet exist. Entire ecosystems instead became the victims of environmental changes unfolding across generations. What survives in the rocks reveals a planet capable of astonishing violence, but also remarkable resilience. Forests eventually return to landscapes buried beneath ash. Rivers carve new valleys through hardened lava. Fresh soils support new plant communities. Animals recolonize devastated regions. Even after the greatest eruptions, life begins rebuilding almost immediately, though often along paths very different from those that came before. Still, there are moments when volcanic fire is only one part of a much larger transformation. As ice ages end and climates warm, another force begins reshaping the world with equal determination. It arrives not from beneath the earth, but from the oceans themselves, advancing shore by shore until entire landscapes disappear beneath rising water, leaving only submerged traces for future generations to discover. The shoreline is retreating, but no one standing beside the water fully understands what they are witnessing. Each generation notices only small changes. A familiar beach becomes narrower. Salt water reaches farther into a river during high tides. Marshes slowly replace dry meadows. A fishing ground shifts beyond the horizon. Families rebuild their homes a little farther inland, believing the sea has simply been unusually restless for a few years. Yet the change never stops. Century after century, the water continues its quiet advance, until forests vanish beneath the waves, valleys become estuaries, and entire landscapes disappear from memory. Unlike earthquakes or volcanic eruptions, rising seas rarely announce themselves with dramatic violence. They are patient. Their power lies not in sudden destruction, but in relentless persistence. Over hundreds and thousands of years, coastlines that once seemed permanent are redrawn again and again. Villages become islands. Islands become reefs. Plains become shallow bays. The transformation is so gradual that those living through it often adapt without realizing they are participating in one of Earth's greatest environmental revolutions. The story begins near the end of the last ice age around 20,000 years ago, when enormous ice sheets covered much of North America, northern Europe, and parts of Asia. These glaciers contained staggering amounts of frozen water. Because so much of Earth's water was locked within continental ice, global sea levels stood more than 100 meters lower than they do today. Vast stretches of continental shelf now hidden beneath modern oceans formed dry land. These submerged landscapes were not empty. They supported rivers, grasslands, forests, wetlands, and the animals that depended upon them. Herds of mammoths, bison, horses, and reindeer crossed regions now lying beneath the North Sea. Human communities hunted, gathered plants, followed migrating animals, and established seasonal camps across territories that have since vanished beneath salt water. To them, these lands were simply home. One of the most remarkable of these lost regions is now known as Doggerland. During the late Pleistocene and early Holocene, it connected what are now Britain, the Netherlands, Denmark, and parts of northern Germany. Rather than an expanse of open sea, the area contained rolling hills, freshwater lakes, winding rivers, marshes and woodlands, rich in wildlife. Archaeologists reconstruct this vanished landscape through sediment cores, seismic surveys, fossil remains, and artifacts recovered accidentally by fishing vessels and offshore dredging operations. Fragments of worked flint antler tools, animal bones, and even traces of ancient peat emerge from the seabed, silent evidence that thousands of people once lived where fishing boats now cross deep water. What survives in the record suggests that Doggerland was not an isolated wilderness, but an important crossroads, linking populations across northwestern Europe. Its disappearance unfolded over thousands of years. As Earth's climate gradually warmed, the great ice sheets began melting. Meltwater poured into the oceans, raising sea levels across the globe. The process was not perfectly steady. Geological evidence indicates that periods of relatively gradual rise were interrupted by episodes known as meltwater pulses, when vast quantities of ice entered the oceans within comparatively short intervals. These events accelerated shoreline retreat, forcing ecosystems and human populations to adjust more rapidly than before. Scholars continue to debate the precise rates and regional impacts of these meltwater pulses because local geography greatly influenced how coastlines responded. In some places, land itself rebounded upward after being released from the immense weight of continental ice, partially offsetting rising seas. Elsewhere, low-lying plains disappeared beneath advancing water with little natural protection. The evidence remains incomplete, but the overall trend is unmistakable. The world map changed dramatically within only a few thousand years. For communities living along ancient coasts, these transformations must have seemed both gradual and relentless. Rivers altered their courses as estuaries expanded. Freshwater wetlands became tidal marshes. Familiar hunting grounds shrank. Migration routes shifted. Some settlements were abandoned voluntarily as resources changed. Others may have been lost more suddenly during storms or unusually high tides. The archaeological record preserves only fragments of these experiences. Organic materials decay rapidly beneath many environments, while repeated marine erosion destroys countless sites before they can ever be discovered. Yet underwater archaeology continues revealing surprising traces of these vanished worlds. Stone tools appear on submerged seabeds. Ancient forests remain preserved beneath layers of marine sediment, their stumps still rooted in the soils where they once grew. Divers occasionally encounter peat deposits containing pollen seeds and insect remains that reconstruct ecosystems long hidden beneath the waves. Similar stories emerge far beyond Europe. Across Southeast Asia, lowered sea levels during the Ice Age exposed an enormous landmass known as Sunderland. Present-day islands, including Borneo, Java and Sumatra, were connected to mainland Asia through extensive plains crossed by great rivers. Tropical forests covered large portions of the landscape, supporting diverse animal populations and early human communities. As sea levels rose, these connections gradually disappeared, creating the island geography familiar today. The flooding of Sunderland transformed both ecosystems and human migration. Populations became increasingly isolated as rising water divided former land routes. Animal species followed separate evolutionary paths on newly formed islands. Marine environments expanded into areas that had once supported terrestrial life. Although scholars continue investigating the precise timing of population movements, the geological evidence clearly demonstrates that some of humanity's earliest coastal landscapes now lie beneath shallow seas. Elsewhere, the narrow land bridge connecting Siberia and Alaska, known as Beringia, experienced its own complex history. During periods of low sea level, this broad expanse allowed animals and humans to move between Asia and North America. Grasslands stretched across what is now the Bering Strait. As glaciers melted, rising seas gradually submerged much of this corridor, leaving only scattered islands above the surface. The flooding altered migration routes, forever isolating populations that had once shared continuous landscapes. These submerged worlds challenge modern assumptions about the archaeological record. Much of humanity's early coastal history may simply be underwater. Ancient shorelines were attractive places to live, offering abundant food, freshwater transportation routes, and relatively mild climates. Yet those same advantages make such sites difficult to study today, because the oceans now conceal them beneath layers of sediment. Technology is slowly changing that picture. High-resolution sonar maps reveal buried river valleys beneath the seabed. Seismic imaging uncovers ancient lake basins and floodplains. Remotely operated vehicles investigate submerged landscapes once thought inaccessible. Each discovery expands understanding of how dramatically Earth's surface has changed since the end of the Ice Age. Still rising seas are only one expression of water's immense power. Occasionally, the ocean does not advance gradually over centuries. Instead, it arrives in a single terrifying surge. Entire coastlines vanish beneath towering walls of water, generated by earthquakes, landslides, or collapsing volcanoes. In those moments, the geological record captures scenes of almost unimaginable violence, preserving evidence of waves so enormous that they carried massive boulders inland, reshaped entire shorelines, and left unmistakable signatures within the rocks that still puzzle researchers today. For countless generations, the coastline offers familiarity. Fishing grounds lie just beyond the breakers. Freshwater streams reach the sea through quiet marshes. Children learn the rhythm of the tides before they can understand the seasons. The horizon remains unchanged through decades of ordinary life, creating the comforting illusion that the ocean always behaves according to predictable rules. Then, in a matter of minutes, that certainty disappears. The sea suddenly withdraws. Boats settle awkwardly onto the exposed seabed. Fish thrash across wet sand where water stood only moments earlier. Shell-covered rocks that no living person has ever seen emerge into the sunlight. To those unfamiliar with what follows, curiosity may overcome caution. People walk toward the retreating shoreline, gathering stranded fish, or staring at the impossible emptiness stretching toward the horizon. Far beyond sight, an enormous wave is already moving toward land. Unlike ordinary wind-driven waves, a tsunami contains energy throughout the full depth of the ocean. In deep water, it may travel at the speed of a commercial aircraft while remaining almost invisible to ships passing overhead. Only when the wave approaches shallower coastal waters does its true scale become apparent. The front slows the water behind, continues pushing forward, and an immense wall of moving sea begins rising above the shoreline. Modern history has witnessed several devastating tsunamis, providing invaluable insight into how these events unfold. The Indian Ocean tsunami of 2004 and the Tohoku tsunami of 2011 demonstrated the extraordinary reach of such waves. Entire communities disappeared within minutes. Ports, roads, forests, and farmland were swept away beneath surging water, carrying ships, vehicles, buildings, and countless fragments of the landscape itself. Yet even these tragic events represent only part of the story recorded in Earth's rocks. Geologists have discovered evidence of ancient tsunamis, whose scale rivals or exceeds anything observed in recent centuries. Their signatures appear in places where ordinary storms could never have deposited the materials found there. Huge boulders weighing hundreds or even thousands of tons rest far above present sea level. Layers of marine sand extend deep into coastal forests. Coral fragments lie scattered across elevated terraces. Microscopic marine organisms appear within inland sediments where they should never naturally occur. Each clue points toward extraordinary waves capable of transporting enormous quantities of material across landscapes in a remarkably short time. One of the most dramatic examples comes from Norway approximately 8,000 years ago. Known as the Storegga Slide, this event did not begin with an earthquake directly beneath a coastline. Instead, a vast section of the continental slope beneath the Norwegian Sea suddenly collapsed. Thousands of cubic kilometers of sediment rushed downslope in one of the largest submarine landslides ever identified. The displaced water generated tsunamis that radiated across the North Atlantic. Evidence of these waves survives along the coasts of Norway, Scotland, Greenland, and the Faroe Islands. Marine sediments appear well above ancient shorelines. Sand layers interrupt peat bogs that had accumulated peacefully for centuries before being abruptly inundated by seawater. Radiocarbon dating links these deposits to the same remarkable event. The timing of the Storegga tsunami is especially intriguing because it coincides with the final stages of flooding across Doggerland. Scholars continue debating exactly how severely the tsunami affected the remaining inhabitants of that low-lying landscape. No single explanation fully accounts for the archaeological evidence, and the gradual rise of sea levels had already transformed much of the region. However, many researchers consider it plausible that such an immense wave devastated surviving coastal communities, accelerating the abandonment of territories already under environmental pressure. If so, one geological catastrophe may have delivered the final blow to a landscape that had been shrinking for centuries. Elsewhere in the world, similar evidence appears in surprising places. On islands throughout the Pacific, enormous coral boulders sit hundreds of meters inland far beyond the reach of ordinary storms. Some weigh more than large houses. For decades, scientists debated whether exceptional hurricanes alone could explain their presence. Detailed investigations now suggest that at least some were transported by prehistoric tsunamis generated through major earthquakes or volcanic collapses. Japan preserves one of the richest records of ancient tsunami deposits. Along parts of its coastline, repeated layers of marine sand separated by ordinary soils reveal a long history of catastrophic inundations extending back thousands of years. Before the devastating Tohoku tsunami of 2011, these ancient deposits already warned that exceptionally large waves had struck the region many centuries earlier. Unfortunately, historical memory often fades more quickly than geological evidence. The rocks remembered what societies gradually forgot. One of the greatest challenges in studying prehistoric tsunamis lies in distinguishing them from powerful storm surges. Both can carry marine sediments inland. Both reshape coastlines. Both leave behind deposits of sand and debris. Researchers therefore examine multiple lines of evidence together: grain size, fossil content, sediment structure, inland extent, elevation, associated boulders, and regional geological context. Even then, uncertainty remains. Scholars still debate the origins of several remarkable coastal deposits around the world. Some researchers favor tsunami interpretations, while others argue for exceptionally intense storms or combinations of multiple processes acting over long periods. Such debates reflect the complexity of Earth's history rather than weakness in the science itself. The geological archive rarely presents perfectly labeled pages. Instead, it offers fragments that must be assembled with careful attention to both evidence and uncertainty. Some of the most spectacular tsunami deposits occur far from modern coastlines because sea levels have changed dramatically since they formed. Ancient marine sediments discovered inland may represent coastlines that existed thousands or millions of years ago rather than today's shores. This shifting geography complicates interpretation, while also revealing how dynamic Earth's surface truly is. Water possesses another remarkable ability beyond transporting sediment. It can preserve moments of catastrophe with astonishing precision. In several coastal environments, tsunami deposits have sealed archaeological sites beneath protective layers of sand and mud. Buildings, tools, plant remains, and even footprints survive because rapid burial shields them from later erosion. Ironically, the same waves that destroyed settlements sometimes created the conditions necessary for their preservation across millennia. These discoveries blur the distinction between destruction and memory. Every catastrophe erases something, yet it also leaves behind traces that future generations may eventually uncover. The geological record is not simply a catalogue of disasters, it is a vast archive created by disaster. Still, even the greatest tsunami depends upon an earlier source of energy. Earthquakes rupture faults. Volcanoes collapse into emptied magma chambers. Massive landslides plunge into the sea. But there are times when the force driving global transformation rises from much deeper beneath the continents themselves, where enormous reservoirs of molten rock accumulate over millions of years. Their eruptions are measured not in individual mountains, but across entire regions, pouring out rivers of lava that reshape landscapes, alter the atmosphere, and prepare the stage for some of the most profound biological crises in Earth's long history. Most volcanic eruptions leave behind a mountain. A cone rises above the surrounding landscape, its slopes built layer upon layer by ash lava and shattered rock. Even the largest familiar volcanoes occupy relatively modest areas when viewed from space. Their influence may extend across valleys or regions, but the eruption itself remains centered on a single mountain. The rocks preserve evidence of something far more difficult to imagine. There are moments in Earth's history when the crust itself seems to split open across enormous distances. Instead of one volcanic peak, hundreds of fissures release molten rock almost simultaneously. Lava does not simply flow downhill from a crater. It spreads across entire provinces, filling valleys, burying forests, damming rivers, and creating landscapes so vast that the horizon disappears beneath fresh basalt. These are the flood basalt eruptions, among the largest volcanic events the planet has ever experienced. Unlike the sudden violence of an explosive eruption, flood basalts often unfold through repeated pulses over hundreds of thousands or even millions of years. Individual eruptions may continue for months or years, followed by quieter intervals before new fissures open elsewhere. From a human perspective, each eruption would be catastrophic. From a geological perspective, they form only one chapter in an immense sequence that slowly transforms continents. Today, these ancient lava provinces appear as broad plateaus, layered cliffs, and dark volcanic plains. Their true scale becomes apparent only when geologists reconstruct the portions that erosion has removed. Many originally covered areas larger than entire modern nations. Some extended across millions of square kilometers. One of the most famous examples is the Deccan Traps of western and central India. Around 66 million years ago, immense quantities of basaltic lava erupted repeatedly across the region. Layer after layer accumulated until some sequences exceeded 2 kilometers in thickness. What survives today represents only part of the original volcanic province, as erosion has removed vast amounts of rock over millions of years. At nearly the same moment in geological history, another extraordinary event occurred. A large asteroid struck what is now the Yucatan Peninsula, producing the Chicxulub impact and contributing to the extinction that ended the age of the non-avian dinosaurs. The coincidence has fueled decades of scientific investigation. Which event played the greater role in the mass extinction? Current evidence suggests that both may have contributed, although not necessarily in identical ways. The asteroid impact delivered an immediate global shock through firestorms, earthquakes, tsunamis, and atmospheric debris. Meanwhile, the Deccan eruptions released enormous volumes of volcanic gases over extended periods, gradually altering atmospheric chemistry and climate. Scholars continue debating the precise interaction between these events. Some studies argue that the asteroid delivered the decisive blow to ecosystems already stressed by volcanic activity. Others emphasize the overwhelming effects of the impact itself. No single explanation fully accounts for every observation, but mainstream research increasingly considers the possibility that Earth's biosphere faced multiple overlapping environmental pressures during this critical interval. The Deccan traps are not unique. Far older volcanic provinces reveal eruptions on an even more astonishing scale. Approximately 252 million years ago, enormous fissure eruptions created the Siberian traps across what is now northern Russia. Over immense spans of time, lava buried forests, wetlands, and river systems beneath repeated flows. In some regions, molten rock intruded into thick deposits of coal, petroleum, and other carbon-rich sediments. This interaction may have dramatically increased the release of greenhouse gases and toxic compounds into the atmosphere. The timing is striking because it coincides closely with the Permian-Triassic mass extinction, the most severe biological crisis known in Earth's history. Roughly 90% of marine species and around 70% of terrestrial vertebrate species disappeared. Entire ecological communities collapsed. Reef systems vanished. Recovery required millions of years. The evidence linking the Siberian traps to this extinction has grown increasingly strong, though many details remain under investigation. Researchers analyze volcanic rocks, carbon isotope records, mercury concentrations, fossil distributions, and climate models to reconstruct the sequence of events. What survives in the geological archive suggests that the eruptions triggered cascading environmental changes rather than a single catastrophic moment. Temperatures rose significantly. Ocean circulation weakened. Large areas of the sea lost oxygen. Acidification placed additional stress on marine organisms already struggling with warming waters. On land, shifting climates altered rainfall patterns, vegetation and habitats across vast regions. This pattern reveals an important truth about Earth's greatest catastrophes. Some apocalypses arrive in an afternoon. Others unfold across thousands of generations. For the animals living during the Siberian eruptions, the disaster would not necessarily have appeared as one dramatic event. Instead, each generation inherited a world subtly different from the one before. Forests retreated. Rivers changed course. Familiar species became increasingly scarce. Weather patterns grew less predictable. Habitats fragmented. Eventually, ecological networks that had persisted for millions of years could no longer sustain themselves. The rocks record these slow collapses with remarkable detail. Volcanic layers alternate with fossil-bearing sediments, allowing scientists to compare ecosystems before, during, and after periods of intense volcanic activity. Chemical signatures preserved within ancient shells reveal changing ocean temperatures. Tiny fossil spores indicate widespread forest destruction. Mercury anomalies found in sediments across multiple continents point toward massive volcanic emissions. None of these clues alone tells the complete story. Together, they form one of the strongest cases in geology for a prolonged environmental crisis driven largely by deep Earth processes. Remarkably, the same volcanic activity responsible for destruction also contributed to renewal. Fresh basalt gradually weathers into mineral-rich soils that can support highly productive ecosystems. Some of the world's most fertile agricultural regions now occupy ancient lava flows. Vineyards flourish on volcanic slopes. Dense forests reclaim once barren landscapes. Rivers carve spectacular canyons through hardened basalt, exposing the layered history of eruptions that ended millions of years ago. This recurring pattern appears throughout Earth's history. Forces capable of devastating life also create the conditions for future diversity. Volcanism influences the atmosphere in more subtle ways as well. Carbon dioxide released from Earth's interior plays an essential role in the long-term carbon cycle. Without volcanic emissions replacing carbon gradually locked away in rocks, Earth's climate would evolve very differently over geological timescales. The same processes that occasionally contribute to environmental crises also help maintain conditions suitable for life across billions of years. Such contradictions define much of the geological record. Creation emerges from destruction. Stability follows upheaval. Extinction opens ecological opportunities for survivors. Yet not every planetary catastrophe originates from within the Earth. Sometimes the source arrives silently through space. For millions of years, asteroids and comets cross Earth's orbit unnoticed. Most are tiny, burning harmlessly through the atmosphere as brief streaks of light. A few survive long enough to produce local damage, but on exceedingly rare occasions an object several kilometers wide approaches the planet. It carries energy beyond anything generated by earthquakes, volcanoes, or tsunamis alone. When such a visitor strikes the rocks, record an apocalypse unlike any other one written not by the slow workings of Earth's interior, but by a single violent collision between worlds. For most of Earth's history, the sky appears empty. The sun rises and sets with quiet reliability. The moon changes its familiar shape from night to night. Stars drift across the seasons in patterns that seem timeless. Meteors occasionally flash overhead, vanishing before anyone can fully comprehend what they have seen. These brief streaks of light rarely inspire fear because they leave no lasting mark upon the landscape. Yet the solar system is far from empty. Millions of rocky fragments travel through space on paths that occasionally intersect Earth's orbit. Most are so small that the atmosphere destroys them high above the ground. Some survive as meteorites scattering harmlessly across deserts, oceans, or forests. Very rarely, however, a much larger object arrives. When an asteroid or comet several kilometers across strikes the planet, the event unfolds with a violence that exceeds ordinary human imagination. Unlike volcanic eruptions or earthquakes, impact events provide almost no warning. There is no slow build-up of pressure beneath the surface, no centuries of gradual environmental change, no visible fault quietly storing energy. A world can pass from apparent normality to catastrophe within minutes. The object enters the atmosphere traveling many times faster than the speed of sound. Friction compresses the air ahead of it until temperatures rise to extraordinary levels, but the greatest danger is not the heat generated during entry. It is the unimaginable kinetic energy carried by a mass moving at tens of kilometers every second. The collision lasts only moments. Solid rock behaves less like stone and more like liquid under such extreme conditions. The impact excavates an enormous crater almost instantly. Bedrock vaporizes. Surrounding material melts or is hurled high above the atmosphere. Shock waves race through the crust, triggering earthquakes that may be among the largest the planet has ever experienced. If the impact occurs in shallow seas, colossal tsunamis radiate outward across entire ocean basins. The atmosphere itself becomes part of the disaster. Fragments of molten rock launched into space begin falling back through the sky over vast regions. As they re-enter the atmosphere, they heat the surrounding air, potentially igniting widespread wildfires. Dust, soot, sulfur-rich gases and vaporized rock spread around the globe, reducing the amount of sunlight reaching Earth's surface. Temperatures decline, photosynthesis weakens, food webs begin collapsing from their very foundations. For decades, many scientists struggled to explain one of the most abrupt biological transitions preserved in the fossil record. At the boundary separating the Cretaceous and Paleogene periods approximately 66 million years ago, countless species disappear with startling suddenness. The non-avian dinosaurs vanish, large marine reptiles disappear, flying pterosaurs are never seen again, ammonites which had flourished in the ancient oceans for hundreds of millions of years abruptly reach their end. Yet crocodilians survive, turtles endure, birds continue as the only living dinosaurs. Mammals, once relatively small and ecologically overshadowed, begin expanding into newly vacant environments. The fossil record clearly documented the extinction. The cause remained uncertain. A major breakthrough arrived in the late 20th century when researchers studying the boundary layer discovered unusually high concentrations of iridium, an element relatively uncommon within Earth's crust but more abundant in many meteorites. This thin clay layer appeared at numerous locations around the world. Something extraordinary had happened simultaneously across the planet. Soon afterward came another remarkable discovery. Buried beneath younger sediments on the Yucatan Peninsula lay an enormous circular structure approximately 180 kilometers across. Detailed geophysical investigations revealed all the hallmarks of a gigantic impact crater. It became known as Chicxulub. Subsequent research linked the crater closely with the iridium layer shocked quartz crystals, microscopic glass spherules, and other impact-related materials preserved worldwide. Together, these independent lines of evidence formed one of the strongest multidisciplinary cases in modern geology. Today, the Chicxulub impact is widely accepted as a principal driver of the end Cretaceous mass extinction. Even so, many important details remain actively investigated. Scholars continue examining how the impact interacted with ongoing environmental stresses, including the immense volcanic eruptions of the Deccan Traps discussed earlier. The evidence suggests that ecosystems were already experiencing pressures before the asteroid struck, although no single explanation fully accounts for every aspect of the extinction pattern. One remarkable feature of the geological record is how rapidly life begins responding after catastrophe. Within years, ferns spread across devastated landscapes. Their spores appear in unusual abundance immediately above the extinction boundary at many sites, creating what researchers sometimes describe as a fern spike. Much like modern plants colonizing landscapes after volcanic eruptions or wildfires, these hardy species rapidly occupied disturbed environments while more complex ecosystems slowly recovered. Recovery itself was anything but immediate. Marine food webs required hundreds of thousands of years to regain complexity. Coral reefs remained greatly diminished. Forest ecosystems reorganized as surviving plant groups expanded into newly available habitats. Mammals gradually diversified into ecological roles previously dominated by dinosaurs. Birds radiated into numerous forms. Over millions of years, entirely new biological communities emerged from the ruins of the old. The rocks preserve these transitions layer by layer. Below the boundary, dinosaur fossils remain relatively common in suitable deposits. Above it, they disappear, replaced by an increasingly different world. This abrupt shift makes the Cretaceous-Paleogene boundary one of the clearest markers in Earth's geological archive. Yet Chicxulub is not the only impact recorded in stone. Across the planet, scientists have identified nearly 200 confirmed impact structures, although erosion, plate tectonics, and sediment burial have undoubtedly erased many more. Some are small craters only a few hundred meters across. Others span dozens of kilometers. Ancient impacts preserved within heavily deformed rocks hint that the early Earth experienced collisions far more frequently than today. One particularly dramatic example is the Vredefort structure in South Africa, currently the largest confirmed impact structure known on Earth. Although erosion has removed much of the original crater, geological evidence indicates that the impact occurred roughly 2 billion years ago and may have created a crater several hundred kilometers wide. At that immense age, almost every direct surface feature has disappeared, Yet the deep scars remain detectable through careful geological investigation. The rarity of large impacts often creates the mistaken impression that they belong only to the distant past. In reality, Earth continues traveling through a dynamic solar system. Space agencies around the world actively monitor near-Earth objects whose orbits approach our planet. The overwhelming majority pose no immediate danger, and no known large asteroid threatens Earth in the foreseeable future. Even so, planetary defense has become an important scientific field, precisely because geological history demonstrates that impacts, while exceedingly infrequent on human timescales, are genuine natural processes rather than hypothetical possibilities. The rocks offer quiet reassurance alongside their warning. They show that life has endured every confirmed impact in Earth's history. They also reveal that survival often comes at an extraordinary cost. Entire evolutionary lineages disappear forever. Ecological balance resets. Recovery unfolds across spans of time so immense that human civilizations would seem like passing moments by comparison. And yet, astonishingly, even the extinction of the dinosaurs was not the greatest biological catastrophe the rocks remember. Far deeper in the geological archive lies evidence of an event so devastating that almost all complex life on Earth came dangerously close to disappearing altogether, leaving behind a thin sequence of stone that records the darkest chapter in the planet's long history. If the disappearance of the dinosaurs marks the end of one spectacular chapter in Earth's history, an even older catastrophe lies buried much deeper in the rocks. It is less familiar to the public, partly because no towering skeletons capture the imagination in quite the same way. Yet to geologists and paleontologists, this earlier crisis stands alone. It is the closest the planet has come to losing almost everything. The evidence begins quietly. A cliff exposes layer after layer of ancient limestone deposited beneath warm tropical seas more than 250 million years ago. Fossils are abundant. Shells of brachiopods cover the rock. Trilobite survivors of hundreds of millions of years appear alongside corals, crinoids, and countless other marine organisms. The ocean seems astonishingly diverse. Then, within a surprisingly thin interval of rock, the abundance collapses. Species that had flourished for immense spans of geological time simply disappear. Reef builders vanish. Entire families of marine creatures reach their final appearance. Above the boundary, the fossil record becomes strangely empty. The richness of the earlier world is replaced by a far simpler ecosystem struggling to recover. This boundary marks the end of the Permian period and the beginning of the Triassic approximately 252 million years ago. It represents the greatest known mass extinction in Earth's history. Unlike the extinction that ended the age of the dinosaurs, the Permian-Triassic crisis unfolded across multiple interconnected environmental changes. What survives in the geological record suggests that no single catastrophe acted alone. Instead, Earth's climate, oceans, atmosphere, and ecosystems entered a prolonged period of instability that gradually overwhelmed even remarkably resilient forms of life. The scale remains difficult to comprehend. Current estimates indicate that roughly 90% of marine species disappeared. On land, forests collapsed across vast regions, while approximately 70% of terrestrial vertebrate species vanished. Entire evolutionary branches ended forever. Ecosystems that had developed over tens of millions of years unraveled with astonishing speed in geological terms. The oceans reveal some of the clearest evidence. Ancient seafloor sediments preserve chemical signatures showing dramatic declines in oxygen. Many marine environments became hypoxic, containing too little oxygen to support the diverse animal communities that had previously thrived there. In some places, conditions may even have become euxinic, where hydrogen sulfide accumulated in oxygen-poor waters, creating environments lethal to many forms of complex life. Microscopic fossils support this picture. Communities of plankton changed abruptly. Reef-building organisms suffered catastrophic losses. Shell-forming animals struggled as ocean chemistry shifted. Carbon isotope records preserved within marine limestone reveal profound disruptions to the global carbon cycle, indicating that enormous amounts of carbon entered the atmosphere and oceans over relatively short geological intervals. The source of this carbon has been the subject of decades of research. The strongest evidence points toward the immense volcanic activity of the Siberian traps discussed earlier. Repeated eruptions released vast quantities of carbon dioxide directly into the atmosphere. At the same time, magma intruded into thick sedimentary basins containing coal, petroleum, and organic-rich rocks. Heating these deposits likely released additional greenhouse gases, including methane and carbon dioxide, amplifying climatic warming. As temperatures climbed, the oceans responded. Warm water holds less dissolved oxygen than cold water. Ocean circulation weakened, reducing the mixing that normally replenishes deep waters with oxygen from the surface. Marine ecosystems faced multiple overlapping stresses, simultaneously warming temperatures, declining oxygen, changing chemistry, and disrupted food webs. On land, conditions grew equally severe. Fossil pollen and spores indicate widespread forest decline across many regions. River systems became increasingly unstable. Intense rainfall alternated with prolonged drought, in some areas accelerating erosion. Soils degraded, habitats fragmented. The familiar landscapes of the late Permian gradually disappeared. Remarkably, fungi appear to flourish during parts of this interval. For years, some researchers proposed the existence of a global fungal spike, interpreting abundant fungal remains as evidence that decomposers spread rapidly through forests filled with dead vegetation. More recent studies suggest the picture is more complicated. Some of the microscopic structures originally identified as fungal spores may belong to other organisms. Scholars still debate the extent of any worldwide fungal expansion, illustrating once again that the geological archive often preserves fascinating clues without providing complete certainty. The extinction did not affect every organism equally. Some lineages proved unexpectedly resilient. Small adaptable species often survived better than highly specialized ones. Generalist feeders endured conditions that eliminated animals dependent upon stable ecosystems. Burrowing organisms found temporary refuge beneath the surface. Freshwater environments sometimes acted as partial sanctuaries, although they too experienced significant disruption. Among the survivors were the ancestors of groups that would later dominate the Triassic world. One particularly important lineage included the cynodonts, distant relatives of modern mammals. At the time of the extinction, they represented only a small component of terrestrial ecosystems. Yet by surviving one of Earth's darkest biological crises, they inherited opportunities unavailable before the collapse. This pattern appears repeatedly throughout geological history. Mass extinctions eliminate extraordinary diversity, but they also remove ecological barriers. Vacant niches allow surviving groups to diversify into entirely new forms. Evolution accelerates as ecosystems rebuild from simplified beginnings. Recovery after the Permian extinction was painfully slow. Unlike the comparatively rapid rebound following some later crises, full ecological complexity required millions of years to return. Reef systems remained sparse. Marine communities recovered unevenly across different regions. Forest ecosystems gradually reorganized as new plant groups expanded into changing climates. The rocks preserve these prolonged recoveries with striking clarity. Thin sedimentary layers deposited year after year reveal gradual increases in biodiversity rather than sudden renewal. Fossils become more varied only after immense spans of time. There's no single moment when life simply returns to normal. Perhaps there never truly was a return to normal. The extinction permanently altered the direction of evolution. Groups that had dominated for hundreds of millions of years never regained their former importance. Others emerged to occupy ecological roles previously unavailable. Eventually, the Triassic world gave rise to dinosaurs, pterosaurs, marine reptiles, and the earliest true mammals. The biological landscape familiar from later Mesozoic history existed only because the earlier world had disappeared. The geological record therefore tells two stories simultaneously. One is a story of overwhelming loss. The other is a story of extraordinary resilience. Life does not survive because it is invulnerable. It survives because enough diversity remains to begin again even after catastrophes that seem almost total. Yet these ancient extinctions are not merely stories about distant animals and vanished oceans. Long after the greatest biological crises had passed, another species appeared that would eventually confront environmental upheavals of its own. Unlike the trilobites or the dinosaurs, these newcomers possessed memory language and tools. They could observe changing landscapes adapt in remarkable ways, and perhaps even preserve echoes of catastrophe in stories passed from one generation to the next. Their survival would depend not on strength alone, but on an extraordinary ability to reshape their lives as the world around them continued to change. By the time the first members of the human family begin walking across African landscapes, Earth has already endured billions of years of upheaval. Continents have collided and separated more than once. Entire oceans have vanished. Countless species have appeared and disappeared. The greatest mass extinctions belong to an unimaginably distant past. Yet the planet that greets these early humans is anything but stable. Beneath seemingly familiar skies, climates continue shifting. Glaciers continue advancing and retreating. Volcanoes remain active. Rivers repeatedly alter their courses, and coastlines are still being redrawn. Humanity enters a world already shaped by catastrophe. The earliest hominins do not inherit a peaceful environment waiting to be explored. They inherit uncertainty. Africa during the last several million years is a landscape of extraordinary environmental variability. Grasslands expand during cooler, drier periods, only to contract again, as forests reclaim the land during warmer, wetter intervals. Lakes appear across the East African rift before shrinking or disappearing altogether. Seasonal rainfall fluctuates across generations. Animal populations migrate in response to changing vegetation, forcing predators and scavengers to adapt alongside them. Many researchers believe this environmental instability plays a significant role in human evolution. Rather than evolving within one stable habitat, early members of the human lineage repeatedly confront changing conditions that reward flexibility. The ability to exploit different food sources, travel across unfamiliar terrain, cooperate in groups, and develop increasingly sophisticated tools becomes more valuable than narrow specialization. Scholars still debate exactly how strongly climate variability drives evolutionary change, but what survives in the fossil and archaeological records suggests that adaptability becomes one of humanity's defining characteristics. The rocks preserve these ancient landscapes in remarkable detail. Layers of volcanic ash scattered across East Africa allow archaeologists to date fossil sites with impressive accuracy. Ancient lake sediments contain pollen grains that reveal shifting vegetation. Stable isotope analysis of fossil teeth records changes in diet as grasslands replace forests and later give way once more to mixed environments. Even microscopic dust particles trapped within sediment cores testify to cycles of drought and rainfall extending across hundreds of thousands of years. These clues reveal that human evolution unfolds not during environmental stability, but amid continual change. One of the most dramatic examples occurs during the repeated glacial cycles of the Pleistocene. Beginning roughly 2.5 million years ago, Earth's climate enters a rhythm of advancing and retreating ice sheets. Massive glaciers spread across northern continents during cold periods, before melting during warmer interglacials. Sea levels rise and fall by more than 100 meters. Rivers carve new valleys during low sea levels, while coastlines migrate inland as glaciers melt. To later civilizations, these changes would have seemed almost unimaginable. For Paleolithic hunter-gatherers, however, they simply represent the world as it exists. Human populations respond with movement rather than permanence. Groups follow migrating herds across expanding grasslands. As climates become harsher, some regions are abandoned while others become refuges rich in water and vegetation. Archaeological evidence from caves, river valleys, and open-air camps suggests remarkable flexibility in settlement patterns. There is no single homeland that remains ideal forever. Instead, survival often depends upon mobility. Among the many challenges faced by early humans, one of the most significant may have been prolonged drought. Sediment cores extracted from ancient African lakes reveal repeated episodes in which water levels declined dramatically. Some lakes fragmented into smaller basins, others nearly disappeared. Vegetation shifted accordingly, altering the availability of food and freshwater resources. Populations living around shrinking lakes would have encountered increasing competition, forcing some groups to migrate while others adapted locally. The exact relationship between these environmental stresses and human evolution remains an area of active research. No single explanation fully accounts for the emergence of modern human behavior. Nevertheless, the evidence increasingly supports the view that fluctuating climates repeatedly influence migration, innovation, and survival. Around 70,000 years ago, Homo sapiens is no longer alone. Neanderthals occupy much of Europe and Western Asia. Denisovans inhabit parts of Asia, although their full geographic range remains uncertain because their fossil record is limited. Smaller-bodied Homo floresiensis survives on the Indonesian island of Flores. Other human relatives may still persist in isolated regions. The human family is diverse, yet over the following tens of thousands of years that diversity gradually disappears. Modern humans become the only surviving human species, exactly why remains one of paleoanthropology's most fascinating questions. Competition likely plays a role. So do differences in population size, technology, social networks, and environmental adaptability. Interbreeding also complicates the picture. Genetic evidence demonstrates that modern humans carry small percentages of Neanderthal DNA outside Africa and Denisovan ancestry in several Asian and Oceanian populations. These discoveries reveal that extinction was not always complete replacement. Some populations merged before disappearing as distinct groups. Climate change may have intensified these interactions. Neanderthal populations repeatedly experienced rapid climatic oscillations across Ice Age Europe. Forests expanded and contracted. Open grasslands alternated with colder steppe environments. Animal distribution shifted, affecting hunting opportunities. Archaeological evidence suggests that Neanderthals successfully adapted to many of these changes for hundreds of thousands of years, making simplistic explanations for their disappearance increasingly difficult to support. Scholars continue debating the balance between environmental pressures and interactions with Homo sapiens. The evidence remains incomplete, reminding researchers that even relatively recent prehistory retains profound mysteries. Meanwhile, other environmental events continue shaping human history. Volcanic eruptions blanket landscapes with ash. Earthquakes alter river systems. Massive floods carve new channels through previously stable terrain. Coastal communities relocate as sea levels continue rising after the last glacial maximum. None of these changes occur in isolation. Human societies experience them alongside evolving technologies, expanding trade, and increasingly complex social organization. Remarkably, some archaeological sites preserve snapshots of these adjustments. Footprints frozen within ancient volcanic ash reveal families walking together across freshly fallen deposits before later sediments buried the surface. Campsites abandoned during changing climates remain sealed beneath wind-blown sand. Stone tools appear beside the bones of animals adapted to environments that no longer exist. These discoveries emphasize that ancient people rarely experience catastrophe as abstract geological processes. They experienced empty rivers, disappearing forests, changing migration routes, unfamiliar coastlines, unexpected winters, unreliable rainfall. The geological record measures these changes in thousands of years. Human communities experience them through individual lives. Generation after generation, people adapted. Some migrated, some innovated, some vanished. Their resilience became one of the defining features of our species, allowing Homo sapiens to expand into nearly every environment on Earth. Yet adaptation had limits. As agriculture emerged and permanent settlements spread, mobility gradually gave way to investment in specific places. Cities rose beside rivers, coastlines, and fertile plains that had supported life for centuries. These civilizations flourished because the environment appeared dependable. The rocks, however, preserved an older lesson. No landscape remains unchanged forever. Soon, some of humanity's earliest civilizations would discover that lesson for themselves, as droughts, earthquakes, volcanic eruptions, and floods challenged societies that believed they had finally found permanence. The first cities do not emerge in empty wilderness. They rise where nature appears generous and dependable. Broad rivers overflow their banks each year, leaving behind fertile soil. Seasonal rains arrive with reassuring regularity. Nearby hills provide stone for construction. Forests offer timber while surrounding plains support crops and grazing animals. Over generations, communities grow into towns, towns become cities, and cities develop into civilizations that seem destined to endure. Yet beneath this appearance of stability, the same restless planet that shaped prehistoric humanity continues its quiet work. Ancient civilizations often flourish during intervals of relatively favorable climate. Crops become reliable enough to support specialists who no longer spend every day producing food. Trade expands along rivers and coastlines. Monumental architecture becomes possible because stable harvests sustain large populations. Writing emerges to record taxes, harvest trade agreements, and royal authority. From Egypt to Mesopotamia, from the Indus Valley to northern China, environmental predictability provides the foundation upon which complex societies are built. The dependence works both ways. When the environment changes even gradually, the consequences ripple through every level of society. One of the clearest examples comes from the ancient kingdom of Egypt. The civilization owes much of its remarkable longevity to the annual flooding of the Nile. For thousands of years, seasonal inundations deposit nutrient-rich silt across floodplains, replenishing agricultural land without the need for artificial fertilizers. Farmers learn to anticipate the rhythm of the river. Calendars, taxation, and political authority become closely tied to its cycles. But the Nile is never completely predictable. Historical records describe years when floods arrive too weakly, producing poor harvests and food shortages. Other years bring excessive flooding that damages settlements and infrastructure. Longer-term climatic shifts affecting rainfall in the Ethiopian highlands, where much of the Nile's water originates, influence the prosperity of communities hundreds of kilometers downstream. Although Egypt survives numerous environmental fluctuations across millennia, periods of political instability often coincide with reduced agricultural productivity. Environmental stress alone does not explain the rise or fall of dynasties, yet it frequently combines with internal conflict, economic challenges, and external pressures. Scholars increasingly view these collapses as the result of multiple interacting factors rather than a single catastrophic event. A similar pattern appears in Mesopotamia. Between the Tigris and Euphrates rivers, some of humanity's earliest cities develop within fertile alluvial plains. Sophisticated irrigation systems transform arid landscapes into productive farmland. Urban populations expand. Monumental temples dominate skylines. Written language flourishes. Over time, however, irrigation introduces unforeseen challenges. Poor drainage causes salts to accumulate gradually within agricultural soils. Crop yields decline in some regions. At the same time, changing river courses alter access to water and transportation. Political competition between city-states intensifies pressure on already strained resources. Archaeological evidence suggests that environmental degradation contributes to broader patterns of instability, although no single explanation fully accounts for the complex history of Mesopotamian civilizations. The Indus Valley civilization presents another enduring mystery. At its height, it includes remarkable urban centers such as Mohenjo-Daro and Harappa, featuring carefully planned streets, sophisticated drainage systems, standardized construction, and extensive trade networks. Then, over several centuries, beginning around 1900 BCE, many major urban centers gradually decline. For generations, researchers proposed invasion theories to explain the transformation. Modern evidence paints a far more nuanced picture. Archaeological investigations increasingly suggest that shifting river systems, changing monsoon patterns, and evolving economic networks play significant roles. Some rivers that once supported major settlements become less reliable or alter their courses entirely. Populations disperse into smaller communities rather than disappearing altogether. The civilization changes instead of simply collapsing. What survives in the archaeological record suggests resilience alongside decline. People adapt by relocating, altering agricultural practices, and reorganizing settlement patterns. Civilizations rarely vanish overnight. The story of the late Bronze Age collapse around the eastern Mediterranean further illustrates this complexity. Between roughly 1200 and 1100 BCE, several powerful kingdoms experienced dramatic disruption. Palaces burn, international trade contracts, writing systems disappear from some regions, population declines occur in certain areas. For many years, scholars searched for a single cause. Today, the prevailing view emphasizes interconnected crises. Prolonged drought likely reduced agricultural production across parts of the eastern Mediterranean. Earthquakes damaged important urban centers in some regions. Political instability weakened established kingdoms. Trade networks became increasingly fragile. Conflict intensified as societies struggled with mounting pressures. No individual factor alone explains the widespread transformation, but together they produced cascading failures across interconnected systems. Climate evidence supporting prolonged drought comes from cave formations, lake sediments, pollen records, and other geological archives. These independent records indicate that rainfall declined significantly in several parts of the region during critical centuries. Again, the rocks quietly preserve information absent from written texts. Volcanic eruptions occasionally leave their mark on civilizations as well. The eruption of Thera on the island, now known as Santorini during the 2nd millennium BCE, remains one of the largest volcanic events in the eastern Mediterranean during historical times. Ash spread across surrounding regions. Tsunamis affected nearby coastlines. The eruption undoubtedly disrupted maritime communities throughout the Aegean. Exactly how strongly it influenced the decline of the Minoan civilization remains actively debated. Earlier interpretations often attributed the civilization's downfall primarily to the eruption. More recent research suggests a more complicated sequence involving recovery, later political developments, and eventual Mycenaean influence. The eruption represents a major regional catastrophe, but the evidence does not support reducing an entire civilization's transformation to a single volcanic event. This distinction is important. Ancient societies prove remarkably adaptable. Cities are rebuilt after earthquakes. Fields are replanted after floods. Trade routes shift following environmental change. People migrate, innovate, and reorganize. Catastrophe becomes decisive only when multiple stresses accumulate faster than societies can respond. Geology and archaeology increasingly tell the same story. Environmental change creates pressure. Human decisions determine much of what follows. The archaeological record preserves abandoned canals, collapsed irrigation systems, unfinished buildings, buried ports, and settlements relocated to higher ground. These are not merely ruins. They are evidence of people confronting landscapes that no longer behaved as expected. Sometimes they succeeded, sometimes they did not. Even when cities disappeared, memory often remained. Generations passed down stories of overwhelming floods, mountains that exploded, skies that darkened, and lands swallowed by the sea. As centuries became millennia, history blended with symbolism. Real environmental disasters gradually transformed into legends that traveled across cultures, surviving long after the original events themselves had faded from direct memory. The rocks preserve the physical evidence. Human societies preserve the stories. Whether those two archives describe the same ancient catastrophes remains one of the most fascinating questions connecting geology, archaeology, and mythology. Long before historians began recording events on clay tablets or papyrus, people were already telling stories about worlds that had nearly come to an end. Around fires, beside rivers, beneath unfamiliar constellations, memories passed from one generation to the next through spoken tradition. Over centuries, those memories changed. Details blurred, heroes appeared, gods entered the narrative, and symbolic meaning grew alongside historical recollection. By the time many of these traditions were finally written down, they had become myths. Yet beneath their dramatic imagery, some scholars have wondered whether fragments of genuine environmental events still remained. The most widespread of these traditions concerns overwhelming floods. Stories describing immense waters appear across remarkably distant cultures. Ancient Mesopotamian literature tells of a devastating deluge that destroys nearly all life, before a chosen survivor preserves humans and animals. Similar flood narratives appear in later Hebrew tradition in Greek mythology, through the story of Deucalion in parts of South Asia, among several indigenous American traditions, and throughout numerous island cultures scattered across the Pacific. These similarities are striking. The differences are equally important. Each tradition reflects the landscape, climate, and cultural values of the society that preserved it. Rivers dominate some accounts. Oceans dominate others. Divine judgment appears in certain versions, but is entirely absent in others. These stories are not identical copies spreading unchanged across continents. They are independent traditions shaped by local environments and histories. Could they nevertheless preserve distant memories of real floods? Scholars approach this question cautiously. The geological record confirms that catastrophic flooding has occurred repeatedly throughout Earth's history. Glacial lakes have burst through natural dams with extraordinary force. Rivers have overflowed across immense floodplains. Tsunamis have swept far inland. Rising sea levels have gradually submerged coastal landscapes over thousands of years. Every region possesses its own history of destructive water. What remains uncertain is whether specific myths preserve memories of particular geological events. One frequently discussed possibility involves the flooding of the Black Sea during the early Holocene. In the late 20th century, researchers proposed that rising Mediterranean waters may have rapidly entered the Black Sea basin after sea levels rose sufficiently to breach a natural barrier. According to this hypothesis, surrounding populations experienced dramatic flooding that later inspired regional flood traditions. The idea attracted enormous public attention. Subsequent research, however, produced a more complicated picture. Marine Corps sediment studies and shoreline investigations continue to refine understanding of the Black Sea's history. While there is broad agreement that major environmental changes occurred in the region, scholars still debate the timing, speed, and magnitude of the flooding. The evidence remains incomplete, and no consensus links the event directly to later flood myths. This pattern appears repeatedly whenever geology meets mythology. Interesting possibilities emerge. Simple conclusions rarely survive detailed investigation. Another enduring tradition tells of islands or kingdoms swallowed beneath the sea. The story of Atlantis remains the most famous example. Described by the Greek philosopher Plato, Atlantis is portrayed as a powerful island civilization destroyed in a single day and night before disappearing beneath the ocean. For centuries, explorers searched for its remains. Countless theories placed Atlanta everywhere from the Mediterranean to the Caribbean, Antarctica, and even beyond the Atlantic Ocean. Modern scholarship, however, takes a far more restrained view. Most historians regard Plato's account primarily as a philosophical narrative rather than a literal historical record. No archaeological evidence supports the existence of a technologically advanced lost civilization matching the description found in his writings. That does not mean the story emerged in complete isolation from reality. The eastern Mediterranean has experienced powerful earthquakes, volcanic eruptions, tsunamis, and gradual coastal changes throughout recorded history. The eruption of Thera discussed earlier profoundly affected Bronze Age societies. Numerous ancient ports now lie partially submerged because of changing sea levels, tectonic movement, or coastal subsidence. Real geological processes may well have influenced cultural imagination. The leap from these processes to Atlantis itself remains unsupported by evidence. Elsewhere, indigenous traditions sometimes align remarkably well with geological observations. Across parts of Australia, oral histories preserved by Aboriginal communities describe coastlines extending far beyond their modern positions before the sea gradually advanced inland. Some researchers suggest that certain traditions may preserve memories dating back thousands of years to the post-Ice Age rise in sea level. This possibility is extraordinary because it implies the long-term survival of cultural memory across immense spans of time. Even here, careful interpretation is essential. Oral traditions evolve continuously. They cannot simply be treated as unchanged historical documents. Instead, they combine observations, symbolic meaning, cultural identity, and practical knowledge into narratives that remain meaningful across generations. The geological record sometimes provides independent support for elements of these traditions, but it cannot confirm every detail. Volcanic eruptions have also left echoes within cultural memory. Several indigenous communities living near active volcanoes preserve stories describing mountains that breathe fire, reshape valleys, or create new lakes. In some cases, geological dating indicates that eruptions occurred within the period of continuous human occupation, making it entirely plausible that oral traditions retain distant memories of real volcanic activity. North America's Cascade Range provides intriguing examples. Some traditions surrounding peaks such as Mount Mazama appear consistent with the catastrophic eruption that formed Crater Lake approximately 7,700 years ago. Geological evidence confirms the eruption's immense scale. Oral traditions describe dramatic transformations of the mountain. Whether specific narratives preserve eyewitness accounts passed across millennia remains difficult to establish conclusively, but the overlap between geological evidence and cultural memory is compelling. The relationship between myth and catastrophe therefore becomes more interesting than either extreme allows. Not every myth records a geological event. Not every geological event produces a surviving myth. Sometimes the two intersect. Sometimes they do not. The rocks preserve physical processes. Human memory preserves human experience. Together they offer complementary rather than identical archives of the past. Modern researchers increasingly recognize the value of studying both with respect. Geologists provide dating methods, sediment analysis, and environmental reconstruction. Archaeologists investigate settlement patterns and material culture. Anthropologists examine oral traditions within their cultural context. Historians analyze written sources. None of these disciplines alone can fully reconstruct humanity's relationship with ancient disasters. When they work together, however, a richer picture begins to emerge. The Earth has always changed. Human beings have always tried to understand those changes, sometimes through careful observation, sometimes through story, sometimes through both at once. Yet beneath every legend, every flood tale, every memory of fire or darkness lies a more fundamental question. How do scientists actually read these events from stone itself? The answers do not come from dramatic discoveries alone, but from patient work carried out grain by grain, crystal by crystal, isotope by isotope, until silent layers of rock gradually reveal histories that no living witness could ever have observed. A geologist standing before an exposed cliff does not simply see rock. Where most people notice color, texture, or impressive scenery, the trained eye begins separating time into layers. A thin seam of volcanic ash immediately draws attention because it represents a moment rather than an age. A subtle change in grain size suggests that a calm lake suddenly became a fast-moving river. Tiny shell fragments reveal an ancient shoreline. Ripple marks preserved across sandstone indicate water flowing in one direction millions of years ago. Every surface contains clues, but none explain themselves. Reading them requires patience, comparison, and an understanding that every answer must be tested against every other piece of evidence. This careful approach distinguishes modern geology from speculation. No single rock tells the whole story. Instead, scientists combine observations gathered from thousands of locations, each preserving only fragments of Earth's past. Like assembling a shattered mosaic, the picture becomes clearer only when scattered pieces begin fitting together across continents. The first task is establishing age. For much of human history, determining the relative order of events depended entirely on simple observation. A layer buried beneath another was assumed to be older. This principle, known as superposition, remains one of geology's most fundamental tools. Although it sounds straightforward, its implications transformed science. Sedimentary rocks became historical sequences. Landscapes acquired chronology. Yet relative order alone is not enough. Researchers also seek absolute ages. Volcanic minerals often contain tiny amounts of radioactive elements such as uranium or potassium. These elements decay into different isotopes at precisely measurable rates. By comparing parent and daughter isotopes within carefully selected minerals, geologists calculate when the crystal last cooled from molten rock. This process, known as radiometric dating, provides some of the most reliable ages available for ancient geological events. The technique has revolutionized understanding of Earth's history. Instead of estimating that an eruption occurred long ago, scientists can determine that it took place approximately 74,000 years ago, or 66 million years ago, or 252 million years ago, each with carefully calculated uncertainties. Those numbers are continually refined as methods improve, but they provide the chronological framework upon which modern geology depends. Sedimentary rocks often require different approaches because they form from particles eroded out of older materials. Here fossils become invaluable. Certain microscopic organisms evolve rapidly while spreading across enormous regions of the world's oceans. Because each species exists for relatively limited intervals of geological time, finding them within sedimentary layers allows scientists to correlate rocks separated by thousands of kilometers. A tiny fossil no larger than a grain of sand may connect cliff faces on different continents. Some of the most useful are foraminifera single-celled marine organisms that build intricate calcium carbonate shells. Although invisible to the naked eye in many cases, their fossils occur in astonishing abundance. Changes in their species through time provide one of the most detailed chronological records available for marine sediments. Pollen grains offer another remarkable archive. Each plant species produces pollen with distinctive shapes visible under high magnification. Lakes, peat bogs, and wetlands quietly accumulate these microscopic particles year after year. By extracting sediment cores and identifying changing pollen assemblages through successive layers, scientists reconstruct ancient vegetation and indirectly ancient climates. A sudden increase in grass pollen may indicate expanding savannas. A decline in tree pollen may suggest widespread forest loss. The return of woodland species can reveal climatic recovery after colder or drier intervals. These records often extend back tens or even hundreds of thousands of years. Ice preserves another extraordinary archive. In Greenland and Antarctica, snowfall accumulates layer upon layer, gradually compressing into solid ice. Tiny bubbles trapped within each annual layer preserve actual samples of ancient atmospheres. By drilling deep ice cores, researchers recover records of greenhouse gases, volcanic ash dust temperature indicators, and even evidence of distant wildfires extending back hundreds of thousands of years. Unlike many geological clues that require indirect interpretation, these air bubbles contain the atmosphere itself. They allow scientists to compare changing concentrations of carbon dioxide, methane, and other gases with shifts recorded elsewhere in the geological archive. Ocean sediments provide yet another perspective. Slowly settling particles accumulate across the seafloor almost continuously. The shells of microscopic organisms, volcanic ash, mineral dust carried by wind, and chemical compounds washed from continents all become incorporated into layered marine deposits. Long cores extracted from these sediments reveal changing ocean temperatures, biological productivity, and environmental conditions spanning millions of years. Even the chemistry of individual atoms contributes to the story. Stable isotope analysis examines subtle variations in elements such as oxygen and carbon. These variations respond predictably to environmental conditions. For example, oxygen isotopes preserved within fossil shells reveal whether ancient oceans were relatively warm or cold. Carbon isotopes help reconstruct disruptions to the global carbon cycle associated with volcanic eruptions, biological crises, or changing ecosystems. None of these techniques operates in isolation. A volcanic ash layer dated radiometrically may coincide with unusual pollen changes, altered oxygen, isotope values, marine extinction patterns, and archaeological evidence of shifting human settlement. Each independent method strengthens the overall interpretation. This convergence is one of the greatest strengths of modern Earth science. When multiple archives point toward the same conclusion, confidence increases substantially. Technology has expanded these capabilities even further. Satellite imagery reveals previously hidden fault systems, buried river channels, and ancient impact structures. Ground-penetrating radar maps archaeological features concealed beneath deserts. Seismic surveys image rock layers several kilometers beneath the surface without excavation. Laser scanning uncovers ancient landscapes beneath dense forest canopies. High-resolution chemical instruments identify trace elements present in concentrations measured in parts per billion. Yet despite these remarkable advances, geology remains rooted in direct observation. Researchers still spend weeks in remote deserts measuring rock layers centimeter by centimeter. They climb mountains to sample ancient lava flows. They collect sediment from lakes using carefully designed coring equipment. They examine fossils under microscopes for countless hours. Every sophisticated laboratory analysis begins with someone standing quietly before a rock face asking what happened here. The process is rarely straightforward. New discoveries frequently challenge long-standing interpretations. Improved dating methods revise familiar timelines. Fresh fossil finds reveal unexpected survival or extinction patterns. Ancient climates prove more variable than previously believed. Science advances not by protecting old ideas, but by continually testing them against new evidence. The geological archive is therefore not a finished book. It is an unfinished investigation. Every expedition uncovers another fragment. Every drill core adds another paragraph. Every analytical technique reveals details invisible to earlier generations. And still enormous mysteries remain. Entire chapters of Earth's history have been erased by erosion or recycled deep into the mantle. Some rock formations continue resisting every attempt at simple explanation. Strange structures appear where they should not. Ancient events leave contradictory signals. The planet has preserved an extraordinary archive, but not a complete one. There are still pages missing from the story. For every geological mystery that has been convincingly explained, another seems to emerge from the rocks. A newly discovered crater raises questions about an unknown impact. An unusual fossil appears far outside its expected range. Ancient sediments preserve chemical signatures that do not fit existing climate models. A mountain range reveals evidence of processes operating far deeper than anyone had imagined. The more carefully scientists read Earth's archive, the clearer it becomes that many chapters remain incomplete. That uncertainty is not a weakness. It is one of the defining characteristics of science itself. The geological record is extraordinarily rich, but it is also imperfect. Wind erases exposed surfaces. Rivers carve away entire formations. Glaciers grind mountains into sediment. Oceans consume old crust through plate tectonics. Heat and pressure transform ancient rocks until their original features become almost unrecognizable. Every process that creates new geological evidence also destroys older evidence. Researchers therefore spend much of their time working with fragments. Imagine attempting to reconstruct the history of an entire civilization after recovering only scattered pages from its libraries. Some pages are burned, others are missing. Entire centuries have vanished, yet enough survives to recognize broad patterns. That is often how geology works. One enduring mystery concerns the timing and pace of abrupt climate change. Ice cores, ocean sediments, cave formations, and lake deposits all demonstrate that Earth's climate can shift far more rapidly than once believed. During the last ice age, particularly in the North Atlantic region, temperatures sometimes change dramatically within only decades. These events, known as Dansgaard-Oeschger events, appear repeatedly throughout glacial records. Exactly why they occurred remains actively studied. Changes in ocean circulation almost certainly played an important role. Variations in fresh water entering the North Atlantic from melting ice sheets may have altered the strength of large-scale currents that distribute heat around the planet. Atmospheric feedbacks likely amplified these changes, yet no single model fully reproduces every feature observed in the geological archive. The rocks clearly show that abrupt shifts happened. Their complete causes remain under investigation. Another remarkable puzzle involves enormous glacial floods. Near the end of the last ice age, vast lakes formed along the margins of retreating continental ice sheets. One of the largest, known as Glacial Lake Missoula, occupied parts of what is now the northwestern United States. Periodically, its ice dam failed. When that happened, an astonishing volume of water surged across the landscape. The resulting floods carved deep channels through basalt plateaus, transported gigantic boulders, sculpted unusual landforms, and left behind gravel deposits, unlike anything produced by ordinary rivers. When geologist J. Harlan Bretz first proposed catastrophic flooding to explain these landscapes during the early 20th century, many scientists rejected the idea. At the time, gradual processes were generally favored over sudden events. Decades later, additional field evidence, aerial photography, and improved understanding of glacial environments confirmed that Bretz had been largely correct. The channeled scablands of Washington state now stand as one of the clearest examples of megaflood erosion on Earth. The episode offers an important lesson. Extraordinary explanations require extraordinary evidence, but they should not be dismissed simply because they describe extraordinary events. The evidence must lead. Interpretations follow. Elsewhere, strange circular depressions scattered across Siberia have recently attracted attention. Some formed after explosive releases of methane beneath permafrost. Others have entirely different origins. Each discovery reminds researchers that Earth's surface continues producing unexpected phenomena even today. Similarly, enormous sinkholes occasionally open without warning where underground limestone dissolves over thousands of years before finally collapsing. Although these events occur on human timescales, their preparation may begin long before recorded history. The landscape often conceals processes that become visible only when they suddenly reach a tipping point. Deep beneath the oceans, additional mysteries remain hidden. Despite decades of exploration, much of the seafloor has never been mapped in high resolution. Ancient river valleys lie buried beneath marine sediments. Submerged volcanoes await detailed investigation. Entire fault systems continue to reveal previously unknown patterns of tectonic activity. The oceans also preserve evidence of underwater landslides capable of generating powerful tsunamis. Yet many of these events remain poorly understood because direct observation is extraordinarily difficult. Space has added another dimension to geological research. Satellite measurements now detect tiny changes in Earth's gravity, revealing hidden structures beneath the surface. Radar penetrates vegetation to expose ancient landscapes concealed beneath tropical forests. Laser mapping uncovers long-forgotten river systems beneath desert sands. Even so, satellites cannot answer every question. Ground truth remains essential. Scientists must still visit remote locations, collect samples, compare observations, and test competing ideas against physical evidence. Among the most fascinating unresolved questions concerns the earliest history of life itself. The oldest widely accepted evidence for life extends back more than 3.5 billion years. Yet exactly when life first emerged remains uncertain. Some ancient rocks preserve structures interpreted as microbial communities. Others contain chemical signatures that may reflect biological activity. Scholars continue debating which evidence is definitive and which might instead result from non-biological geological processes. The distinction matters enormously because it concerns one of humanity's oldest questions. How quickly did life appear once Earth became habitable? The rocks have not yet provided a final answer. Similar uncertainty surrounds several ancient impact structures. Geologists suspect that many large craters have disappeared through erosion or subduction. Some unusual geological formations may preserve deeply buried remnants of impacts no longer recognizable at the surface. Geophysical surveys occasionally reveal circular anomalies that warrant further investigation, but confirming their origin often requires years of detailed study. Not every circular feature is an impact crater. Not every unusual rock formation records catastrophe. Careful testing separates convincing evidence from attractive speculation. This distinction becomes especially important when popular culture embraces dramatic explanations, claims of advanced lost civilizations, mysterious global cataclysms, unsupported by evidence or impossible ancient technologies, often spread far more rapidly than careful scientific research. Genuine geological mysteries are fascinating enough without requiring unsupported additions. Mainstream archaeology and geology remain open to revising conclusions whenever compelling new evidence appears. At the same time, extraordinary claims must withstand equally extraordinary scrutiny. That balance has allowed understanding of Earth's history to grow steadily more accurate with each generation. Perhaps the greatest mystery is not any individual event. It is how many remain undiscovered. Every year new fossil species are described. Previously unknown impact structures are identified. Ancient climates are reconstructed in greater detail. Submerged archaeological landscapes emerge from beneath the sea. Entire chapters of Earth's story continue appearing where no one expected them. The archive is far from complete. It is still being uncovered, and as remarkable as the forgotten past may be, its importance does not end with curiosity alone. The same geological forces that shaped vanished worlds continue operating beneath modern cities, beneath today's oceans, and beneath the feet of billions of people who often assume that the age of great natural catastrophes belongs only to distant history. The rocks never suggest that Earth's age of catastrophe has ended. Instead, they reveal something both reassuring and unsettling. The same forces that buried ancient forests beneath lava lifted seashells onto mountain summits, drowned coastlines beneath rising oceans, and scattered the fossils of vanished worlds continue operating today. Their pace may be slow enough to escape notice during an ordinary lifetime, but the processes themselves have never stopped. Modern civilization often measures time in election cycles, economic trends, or generations. Geology measures it differently. A fault that has remained silent for 800 years may still be considered active. A volcano dormant for 10,000 years may simply be resting. A glacier retreating over a century represents only a brief moment within a much longer climatic rhythm. The planet does not recognize the boundaries that humans place around history. One of the clearest reminders comes from plate tectonics. Every year, continents continue drifting by a few centimeters. Instruments using satellite positioning can measure movements with astonishing precision. The Atlantic Ocean widens slightly. Parts of the Pacific slowly shrink as oceanic crust disappears beneath surrounding continents. The Himalayas continue rising even as erosion simultaneously wears them down. Along the East African Rift, the continent itself is gradually pulling apart, hinting that a new ocean may eventually form millions of years in the future. None of these changes are dramatic from one year to the next. Across geological time, they reshape the entire world. The same quiet accumulation applies to earthquakes. Along major fault systems, rocks on either side rarely slide smoothly past one another. Instead, friction locks them together while tectonic forces continue pushing. Stress builds gradually over decades or centuries. The landscape appears perfectly stable. Then, without warning, the fault ruptures. Within seconds, centuries of accumulated movement are released. Modern examples provide sobering illustrations. The Great Chilean Earthquake of 1960, the largest instrumentally recorded earthquake in history, generated powerful tsunamis that crossed the Pacific Ocean. The Indian Ocean earthquake of 2004 produced waves that affected coastlines across multiple nations. Japan's Tohoku earthquake in 2011 demonstrated how advanced technology and extensive preparation can reduce risk, but cannot eliminate the immense power of geological processes. Each event also contributed valuable scientific knowledge. Careful mapping of tsunami deposits improved understanding of prehistoric events. Measurements of crustal movement refined tectonic models. Sediment studies extended earthquake histories far beyond written records. Every modern disaster becomes another page in Earth's archive. Volcanoes continue providing similar reminders. Mount St. Helens transformed dramatically in 1980, reminding observers that landscapes can change within hours. Pinatubo's eruption in 1991 injected enough sulfur into the atmosphere to produce measurable global cooling for several years. Iceland's Eyjafjallajökull eruption in 2010 disrupted international air travel, illustrating how interconnected modern civilization has become with natural systems. None of these eruptions approach the scale of ancient supervolcanoes or flood basalt provinces, yet they demonstrate that volcanic activity remains an ordinary part of Earth's ongoing history. Climate also continues evolving. Throughout the geological archive, climates have always changed in response to combinations of volcanic activity, orbital cycles, continental rearrangement, greenhouse gas concentrations, ocean circulation, and many other interacting factors. Today's climate changes occur within this long geological context. At the same time, multiple independent scientific disciplines conclude that the rapid warming observed since the Industrial Revolution is driven primarily by human emissions of greenhouse gases superimposed upon Earth's natural climate variability. This conclusion arises not from a single line of evidence, but from observations across atmospheric measurements, ocean temperatures, ice cores satellite records, isotope analysis, and climate modelling. The Geological Archive plays an essential role here. By reconstructing past climates, scientists better understand how Earth's systems respond to changing concentrations of carbon dioxide and other greenhouse gases. Ancient warm periods preserved in rocks offer valuable comparisons, although no past event matches the precise combination of modern conditions. The past does not provide exact predictions. It provides perspective. Another lesson concerns sea level. At the height of the last ice age, coastlines extended far beyond their present positions. During warmer intervals in Earth's deeper history, sea level stood significantly higher than today. These ancient shorelines demonstrate that coastlines have always shifted. Modern observations show that global sea level is once again rising as oceans warm and land ice melts. The exact rate of future change depends upon numerous interacting factors, including future greenhouse gas emissions and ice sheet responses. Here again, geology extends the record beyond direct human observation. Coral reefs, coastal sediments, submerged forests, and ancient beach deposits reveal how shorelines responded to previous climatic transitions. The rocks cannot predict the future with certainty. They do show that coastlines are never permanent. The same is true of ecosystems. The fossil record demonstrates that life repeatedly adapts to changing environments. Species migrate when conditions shift. Some evolve, others disappear. Entire ecological communities reorganize following disturbances. Human civilization now influences these processes in unprecedented ways through habitat alteration, pollution, resource use, and climate change. Understanding past environmental transformations therefore becomes more than an academic exercise. It becomes a guide to understanding resilience and vulnerability. Perhaps the most important message preserved within the Geological Archive is not one of inevitable destruction, but of interconnectedness. Volcanoes influence climate. Climate alters vegetation. Vegetation affects erosion. Erosion reshapes rivers. Rivers carry nutrients into oceans. Ocean circulation influences atmospheric patterns. Every component affects countless others. The same principle applies to human societies. Agriculture depends upon rainfall. Cities depend upon stable infrastructure. Trade depends upon reliable transportation. Modern civilization often assumes that technological sophistication places it outside natural history. The rocks suggest otherwise. Technology changes how people respond to geological processes. It does not remove humanity from the Earth system itself. Despite remarkable advances in engineering, forecasting, satellite observation, and disaster preparedness, the fundamental relationship remains unchanged. Civilizations still build upon landscapes shaped by forces operating over millions of years. Every bridge crosses valleys carved by ancient rivers. Every city rests upon rocks with geological histories extending far beyond recorded time. Every coastline reflects countless earlier advances and retreats of the sea. The planet beneath modern civilization is the same restless Earth that preserved the stories explored throughout this journey. Its cliffs still accumulate new layers. Its volcanoes still breathe. Its oceans still reshape their shores. Its mountains continue rising even while they slowly disappear. And somewhere perhaps beneath an unexplored seabed, or within an isolated desert plateau, new discoveries wait patiently inside the rocks, preserving evidence of catastrophes not yet fully understood, waiting for future generations to uncover the next forgotten chapter in Earth's immense memory. The oldest rocks on Earth possess no voice, yet they have never stopped telling their story. Long before the first human footprint pressed into damp soil, before the earliest campfire flickered beneath an open sky, before the first city rose beside a river, the planet was already writing its history. It wrote with lava instead of ink, with rising mountains instead of monuments, with advancing glaciers instead of armies. Every eruption, every flood, every shifting coastline, every vanished forest became another sentence in an archive so vast that even after centuries of scientific study, only a small portion has been carefully read. What makes this archive extraordinary is not simply its age. It is its honesty. The rocks do not exaggerate. They do not simplify. They preserve moments exactly as physical processes allowed, indifferent to human hopes or fears. A thin layer of volcanic ash says nothing about the emotions of the animals fleeing beneath a darkened sky. A band of marine sediment buried high within a mountain offers no explanation for the countless millions of years required to lift an ancient seabed into the clouds. Fossils do not mourn extinction. They simply remain where life left them, waiting for curious minds to recognize their significance. Human history often feels immense because it contains everything familiar to us. Empires rise and fall. Languages appear and disappear. Religions spread across continents. Trade routes flourish before fading into memory. Wars reshape political boundaries. Entire civilizations transform the landscapes around them. Yet from the perspective of geology, all of recorded history occupies only the thinnest surface layer. If Earth's 4.5 billion years were compressed into a single calendar year, modern civilization would appear only in the final moments before midnight on the last day. The pyramids, the Roman Empire, the great kingdoms of Asia, the Industrial Revolution, and the digital age would all exist within an interval too brief to distinguish without magnification. The realization is deeply humbling. It reminds us that humanity did not arrive on a finished planet. We entered an ongoing story. Every generation inherits landscapes created by events that unfolded long before human memory began. The fertile plains supporting agriculture often consist of sediments carried by rivers over tens of thousands of years. Rich mineral deposits originate from volcanic or tectonic processes operating millions of years ago. Coastlines reflect ancient glacial cycles. Mountain ranges preserve the scars of vanished oceans. Even the air we breathe carries the legacy of ancient geological events. The oxygen filling Earth's atmosphere exists because early life transformed the planet over immense spans of time. Carbon locked within limestone records countless marine organisms that lived and died across hundreds of millions of years. Every handful of soil contains fragments of older worlds recycled through erosion, weathering, and biological activity. Nothing exists in isolation. One of the greatest achievements of modern science has been recognizing these connections. Geologists, paleontologists, archaeologists, climatologists, oceanographers, chemists, physicists, and biologists approach Earth's history from different directions, yet their evidence repeatedly converges. Fossils align with isotopes. Ice cores complement sediment records. Ancient shorelines correspond with changing climates. Archaeological discoveries fit within broader environmental reconstructions. The resulting picture remains incomplete, but it grows steadily clearer. Perhaps the most remarkable lesson concerns resilience. Again and again, the geological archive records extraordinary destruction. Supercontinents fracture. Flood basalts spread across continents. Asteroids transform global ecosystems. Glaciers reshape landscapes. Mass extinctions eliminate most existing species. Entire coastlines disappear beneath rising seas. Yet after every catastrophe, life begins rebuilding. Not immediately, not easily. Sometimes recovery requires millions of years. Nevertheless, recovery comes. New ecosystems emerge. New evolutionary opportunities appear. New landscapes develop. The Earth never returns precisely to what existed before. Instead, it becomes something different. Human societies display a similar pattern. Communities rebuild after earthquakes. Cities rise again following volcanic eruptions. Cultures adapt to changing rivers. Farmers adjust to shifting climates. Knowledge passes across generations, allowing each to learn from earlier experience. History does not erase catastrophe. It incorporates it. This does not mean every civilization survives. The archaeological record makes that painfully clear. Many societies disappear. Languages vanish. Trade networks collapse. Settlements become ruins. Yet humanity as a whole continues adapting just as earlier forms of life repeatedly adapted to changing worlds. There is another quiet lesson hidden within the rocks. Most catastrophes begin long before they become visible. Faults accumulate stress for centuries. Magma slowly gathers beneath volcanoes. Ice sheets expand or retreat over thousands of years. Sea levels rise meter by meter. Climate systems evolve gradually before crossing important thresholds. The dramatic moment often represents only the final stage of processes already underway. Recognizing these long preparations allows science to move beyond simple storytelling. Instead of merely describing disasters after they occur, researchers seek to understand the mechanisms behind them. That understanding improves hazard assessment. It guides conservation. It strengthens engineering. It informs planning. Knowledge cannot prevent every natural disaster. It can reduce unnecessary surprise. The rocks also teach intellectual humility. Many questions remain unanswered. Some chapters of Earth's history have been permanently erased through erosion and tectonic recycling. Others remain hidden beneath oceans or polar ice. Future discoveries will almost certainly revise familiar interpretations. Ideas accepted today may become more refined tomorrow. This continual refinement is not failure. It is how understanding grows. Perhaps somewhere beneath a distant desert lies another impact crater awaiting discovery. Perhaps sediments beneath an unexplored continental shelf preserve evidence of unknown human settlements flooded after the Ice Age. Perhaps future drilling will recover older traces of early life than any yet found. The archive is still incomplete. The investigation continues. Standing before an ancient cliff at sunset, it becomes easier to understand why generations of geologists describe rocks as Earth's memory. Every visible layer represents countless vanished days. Every fossil marks a life once lived. Every mineral crystal cooled from molten depths long before humanity imagined the concept of history. The silence of the landscape is therefore deceptive. Beneath that silence lies a story of unimaginable violence, astonishing resilience, endless transformation, and remarkable continuity. The apocalypse hidden in the rocks is not one single catastrophe. It is the realization that Earth has experienced many endings. Each seemed absolute. None became final. Every ending prepared the conditions for another beginning. And perhaps that is the deepest lesson preserved within the stone itself. The world has never been static. It has never been guaranteed. It has never stopped changing. Neither has life. The cliffs remain where they have always stood, watching seasons pass with quiet patience. Rain falls, rivers flow, tides advance and retreat, and the slow work of weather continues almost unnoticed. A visitor may spend only a few moments before an ancient rock face seeing little more than layers of stone warmed by the afternoon sun. Yet those layers contain memories older than forests, older than mammals, older than the continents as they appear today. There is something comforting in that immense perspective. Human history, remarkable as it is, becomes part of a much longer story rather than standing apart from it. Every civilization has borrowed its foundations from landscapes shaped by countless earlier worlds. Every road, every village, every city rests upon rocks that have witnessed transformations beyond imagination. The planet has endured fire, ice-rising seas, falling mountains, vanished oceans, and skies darkened by ash. It has seen nearly all complex life disappear before slowly flourishing once more. Again and again, destruction has been followed by renewal, Not because catastrophe is gentle, but because time is patient. The rocks ask for patience as well. They reveal their stories slowly, one layer at a time, rewarding careful observation over quick conclusions. Even now, scientists continue uncovering forgotten coastlines beneath the sea, hidden impact craters beneath forests, ancient climates preserved in ice, and fossils waiting quietly inside stone. Each discovery adds another sentence to a history that can never be fully finished. Perhaps that is what makes the geological archive so remarkable. It reminds us that certainty is rare, curiosity is valuable, and the search for understanding never truly ends. As daylight fades across an ancient landscape, the cliffs return to silence. Wind moves through grasses growing above rocks that remember vanished oceans. Stars appear over mountains lifted from forgotten seabeds. Somewhere beneath the surface, continents continue their slow journey, invisible yet unstoppable. The Earth keeps writing its history just as it always has, and the stones patient beyond measure continue remembering.